Max Planck, the reluctant revolutionary. In the dying days of the 19th century, physics seemed complete. Scientists believed they had conquered the natural world with Newton's laws and Maxwell's equations. But one man, working quietly in Berlin, would shatter this confidence and birth an entirely new understanding of reality. His name was Max Planck, and he would become the father of quantum theory, a revolution he never intended to start. The classical world. Born in Kiel, Germany, in 1858, Max Carl Ernst Ludwig Planck grew up in a world of order and precision. His father was a law professor, instilling in young Max a deep respect for logic and tradition. When Planck expressed interest in physics, one of his professors warned him that physics was essentially finished, that all the important discoveries had been made. Fortunately for humanity, Planck ignored this advice. By the 1890s, Planck had established himself as a respected theoretical physicist in Berlin, working on thermodynamics, the study of heat and energy. He was the epitome of a classical physicist, methodical, conservative, and deeply committed to the deterministic worldview that had governed science for centuries. Nothing in his background suggested he would become a revolutionary. The Blackbody problem. Planck's world began to crack in 1894 when he encountered a problem that had stumped physicists for decades: blackbody radiation. A blackbody is an idealized object that absorbs all electromagnetic radiation that hits it. When heated, it emits radiation across a spectrum of wavelengths. Factories and lighting companies desperately wanted to understand this phenomenon to create more efficient light bulbs. Classical physics predicted something absurd. According to existing theories, a heated black body should emit infinite amounts of ultraviolet radiation, the so-called ultraviolet catastrophe. Obviously, this didn't happen in reality. Light bulbs didn't explode in bursts of infinite energy. Something was fundamentally wrong with classical physics. For 6 years, Planck wrestled with this problem. He tried every conventional approach, manipulating equations, adjusting assumptions, searching for a solution within the framework of classical physics. Nothing worked. The mathematics simply wouldn't cooperate with reality. The quantum leap. On December 14, 1900, Planck presented a paper to the German Physical Society that would change everything. Desperate to match theory with experimental data, he had made what he considered a mathematical trick, a temporary assumption he hoped to eliminate later. He proposed that energy wasn't continuous, flowing smoothly like water, but came in discrete packets, little bundles he called quanta. The energy of each quantum was proportional to its frequency, connected by a tiny number that would become one of the most important constants in physics. Planck's constant, symbolized by the letter h. The equation was deceptively simple. E equals h nu, energy equals Planck's constant times frequency. This assumption solved the black body problem perfectly. The mathematics worked. The predictions matched experimental observations. But Planck himself was horrified by what he'd done. He had violated the fundamental continuity of classical physics. For years afterward, he tried desperately to find a way to preserve classical physics while explaining black-body radiation. He failed. The quantum had been born, whether he liked it or not. The quantum revolution. At first, the scientific community largely ignored Planck's work. It seemed like an obscure mathematical curiosity. But in 1905, a young patent clerk named Albert Einstein took Planck's quantum seriously. Einstein used it to explain the photoelectric effect, proposing that light itself came in quantum packets, later called photons. Planck, ironically, thought Einstein had gone too far. Over the next 2 decades, quantum theory exploded. Niels Bohr used it to explain atomic structure. Werner Heisenberg discovered the uncertainty principle. Erwin Schrödinger developed wave mechanics. The quantum revolution Planck had inadvertently started consumed all of physics. Throughout this transformation, Planck remained ambivalent. He had opened Pandora's box, but he struggled with its implications. The quantum world was probabilistic, uncertain, and fundamentally different from the clockwork universe he'd grown up believing in. He once remarked that a new scientific truth doesn't triumph by convincing its opponents, but rather because its opponents eventually die. Legacy and loss. Planck's personal life was marked by tragedy. His first wife died in 1909. During World War I, one son died in battle. Both daughters died in childbirth. During World War II, his remaining son was executed by the Nazis for participating in a plot to assassinate Hitler. Despite these crushing losses, Planck continued his scientific work with quiet dignity. He received the Nobel Prize in Physics in 1918 for his quantum theory. Yet he remained, in many ways, a classical physicist at heart, uncomfortable with the radical implications of his own discovery. He never fully embraced the probabilistic interpretation of quantum mechanics that later physicists developed. Max Planck died in 1947 at age 89, having witnessed his reluctant revolution reshape all of physics. Today, his constant appears in equations throughout quantum mechanics, quantum field theory, and the standard model of particle physics. It governs the behavior of everything from computer chips to DNA molecules. The quantum world. Planck's quantum would prove to be more than just a solution to a thermodynamics problem. It was the first glimpse into a deeper reality where certainty gives way to probability, where observation affects outcomes, and where particles can exist in multiple states simultaneously. Our modern world, with its lasers, semiconductors, MRI machines, and quantum computers, is built on the foundation Planck reluctantly laid. The man who never wanted to be a revolutionary became one of the greatest revolutionaries in scientific history. Max Planck didn't just solve a problem. He discovered that reality itself operates on principles radically different from everything humanity had previously believed. In trying to save classical physics, he destroyed it and gave us the quantum universe.